Catalytic cracking units are important secondary processing units and are units that create significant economic benefits. Today, we will learn about the process flow of catalytic cracking. The catalytic cracking process uses heavy distillates like vacuum gas oil (VGO) and coker gas oil or residual oil as feedstocks under relatively low pressure and at temperatures of 450 to 510 degrees Celsius. A series of chemical reactions occur in the presence of a catalyst, converting them into light products like gas, gasoline, diesel, and coke. Considering the products from various refineries, we can summarize that catalytic cracking products have the following characteristics. 1. High light oil yield, which can reach 70 to 80%. 2. High octane number of catalytic cracked gasoline and good gasoline stability. The octane number of catalytic cracked gasoline can reach about 88 to 93, which is relatively high. Whereas straight run gasoline has an octane number between 40 to 50. So why does catalytic cracked gasoline have such a high octane number? This will also be covered in later knowledge points. Students can also think about it. 3. Catalytic cracked diesel has a low cetane number. It is often blended with straight-run diesel or hydrotreated to improve its cetane number to meet specifications. 4. Catalytic cracked gas C3 and C4 gases account for 80%. Among them, propylene accounts for 70%. Various butylenes in C4 can account for about 55%. They are excellent petrochemical feedstocks and raw materials for producing high-octane components. Good. Next, we will learn about the process flow of catalytic cracking. A catalytic cracking unit consists of the following sections. It can be divided into the reaction regeneration system, fractionation system, absorption stabilization system, regeneration flue gas energy recovery system, and LPG gasoline desulfurization and treating, etc. Among them, the reaction regeneration system is the core part of the catalytic cracking unit. The main types of units are bed reactor riser type. The riser type is further divided into high-low parallel type and coaxial type. Although the reaction regeneration systems of different unit types may have slight differences, their principles are the same below. We will use the high-low parallel riser catalytic cracking as an example to introduce the process flow. The process flow diagram of the reaction regeneration system is shown in the figure. Let's look at the catalytic cracking process flow. Fresh feedstock, generally referring to vacuum gas oil (VGO), is mixed with recycled oil after a series of heat exchanges and enters the heating furnace for preheating. Its temperature can reach about 300 degrees Celsius. It is injected into the lower part of the riser reactor in an atomized state through the feedstock oil nozzles. Slurry oil enters the riser directly without heating. It contacts the high-temperature catalyst from the regenerator temperature. Here can reach 650 to 700 degrees Celsius and vaporizes immediately. The oil vapor, along with atomizing steam and pre-lift steam, carries the catalyst up through the riser at a high linear velocity of 7 to 8 mph. The reaction time is 2 to 4 seconds. After separation by the quick separator, most of the catalyst is separated out and falls into the lower part of the disengager. The oil vapor carrying a small amount of catalyst enters the fractionation system after the entrained catalyst is removed by 2 stages of cyclones. The spent catalyst with coke enters the stripping section below the disengager from the disengager. It is stripped with superheated steam to remove the small amount of oil vapor absorbed on the catalyst surface. The stripped catalyst flows through the spent catalyst standpipe and the spent catalyst plug valve into the regenerator. It contacts air from the bottom of the regenerator. This air is supplied by the main air blower, forming a fluidized bed for the regeneration reaction. Simultaneously, a large amount of combustion heat is released to maintain a sufficiently high bed temperature in the regenerator. The regenerator maintains a top pressure of 0.15 to 0.25 megapascals G. The regenerated catalyst returns to the riser reactor for reuse via the regenerated catalyst standpipe and regenerated catalyst plug valve. The regeneration flue gas produced by coke burning enters the cyclones through the dilute phase section of the regenerator. After most of the entrained catalyst is removed by 2 stages of cyclones, the flue gas is discharged to the stack via the plenum chamber and the double disc control valve. The regeneration flue gas temperature is very high and contains about 5 to 10% HO to utilize its heat. Many units are equipped with co-boilers that use regeneration flue gas to generate steam. For units with higher operating pressure, a flue gas energy recovery system is often installed to utilize the thermal energy and pressure of the regeneration flue gas to drive the main air blower. Saving electricity. Regarding the reaction regeneration system, it needs to be explained that The catalytic cracking reaction is an endothermic process requiring heat, while the reaction in the regenerator is exothermic. Providing the heat, therefore, the catalyst acts as a heat carrier, facilitating the catalytic reaction while also transferring heat through circulation. Secondly, the regeneration flue gas has high temperature and large flow rate. The chemical energy and thermal energy of the regeneration flue gas should be recovered. During production, catalyst is lost and deactivated to maintain the catalyst inventory and activity within the system. It is necessary to periodically supplement or replace the catalyst in the system. Therefore, we can see that ensuring the normal flow direction of catalyst between the two vessels, reactor and regenerator, and good fluidization state in the regenerator are the technical keys of the catalytic cracking unit. Okay, let's look at the fractionation system. The function of the fractionation system is to separate the products from the reaction regeneration system, obtaining some products and semi-finished products. The high temperature oil vapor from the reaction regeneration system enters the lower part of the catalytic fractionator. After being desuperheated in the desuperheating section equipped with baffles, it enters the fractionation section. After fractionation, fuel gas, raw gasoline, light diesel, heavy diesel, recycled oil, and slurry oil are obtained. The fuel gas and raw gasoline go to the absorption stabilization system. Light and heavy diesel are sent out of the unit after heat exchange or cooling. Recycled oil returns to the reaction regeneration system for recycling. A portion of the slurry oil is sent to the reaction regeneration system for recycling. Another portion is circulated back to the fractionator after heat exchange. To remove excess heat from the fractionator and distribute the internal load evenly, 4 circulating refluxes are set at different positions in the tower. Top circulating reflux, first intermediate reflux, second intermediate reflux. And a slurry circulating reflux, the desuperheating section at the bottom of the catalytic fractionator, is equipped with about 10 chevron baffles. Since the feed is superheated, oil vapor above 460 degrees Celsius carrying catalyst powder, it is necessary to first cool the oil vapor to a saturated state and wash down the entrained dust. To facilitate fractionation and avoid clogging the trays, therefore, the slurry oil drawn from the bottom of the tower is cooled and returned above the chevron baffles, contacting countercurrently with the rising oil vapor from the bottom. On one hand, it cools the oil vapor to the saturated state. On the other hand, it washes down the dust entrained in the oil vapor. The fuel gas from the overhead of the fractionator contains gasoline components, while the raw gasoline dissolves C3, C4, and even C2 components. The function of the absorption stabilization system is to use absorption and fractionation methods to separate the fuel gas and raw gasoline into dry gas, LPG, and stabilize gasoline with qualified vapor pressure. Okay? The knowledge points covered in this lesson include the process characteristics of catalytic cracking, the process flow of catalytic cracking, the process characteristics of the reaction regeneration system, the process characteristics of the fractionation system, and the process characteristics of the absorption stabilization system. This is the content of our lesson today. Goodbye, students.